Hello, everyone. Welcome to Pre-Lecture 13. This is going to be our introduction to acids and bases, which is the start of chapter 14 in our textbook. Okay, so acid-base chemistry is some of the most important chemistry out there, and particularly anytime you're dealing with water. Water can dissociate to form protons H plus and hydroxide OH minus. That is incredibly important for a number of reasons that we'll get into in this pre-lecture as well as this unit overall. And we're going to cover multiple definitions for what an acid is and what a base is. And this pre-lecture is going to start with one of those definitions called a Bronsted-Lowry acid and base. And so for Bronsted-Lowry acid, it will donate a proton, so an H plus atom, to a Bronsted-Lowry base, which will then accept a proton. And so in this example here, water, if it were to donate a proton to another water, it would form hydroxide. In this case, ammonia is acting as base, and forms ammonium. So that is acting as a conjugate acid. Okay. And of course, we should define what those terms are. So just as a basic definition, anything that is on the left side of our reaction arrow is either going to be an acid or base. Anything that is on the right side of our reaction arrow is going to be a conjugate acid or a conjugate base. Okay. And so they're essentially still acids and bases in equilibrium. We would just define them as something that is a product in a reaction rather than a reactant. Okay. And so in this reaction shown below, we have water reacting with ammonia. Water is acting as our Bronsted-Lowry acid because it donates a proton to ammonia. And then ammonia, of course, is then acting as base, and then water forms hydroxide, which is the conjugate base, and ammonia forms ammonium, which is then our conjugate acid. Okay. So here's a moment for you to practice, figure out what would be our acid, base, and conjugate base in these examples. If you want to pause the video and do that, I am going to reveal the answers now. So in this case, we have HF reacting with O2 to produce ammonium and hydroxide. On the product side, we should call this the conjugate acid and the conjugate base, and then the conjugate acid and conjugate base for this molecule called pyridine reacting with water as well. Okay. And so this is the slide on the previous, this example, rather we have water acting as a base in our first reaction and acting as an acid in our second. And so this is a property called amphotericity, if we want to just say water is amphoteric, that could be another way to describe it. It's essentially when a molecule can act as both an acid and a base. It just depends on the situation. Okay, and so water is special in that it is amphoteric and it can react with itself to produce H3O+, which is a molecule called hydronium that we talk about, and hydroxide as its conjugate acid and conjugate base. And we can describe this in an equilibrium. And so instead of using Kc, because this is defining a specific thing, we would call it Kw, right? And so when a solution is neutral, it will have the same proportion of H3O+ and OH-, hydronium and hydroxide. If more protons are present, then the solution will be acidic, and if more hydroxide is present, then it would be basic, okay? The most common way to report this ratio is a property called pH. And so all pH is measuring is it is taking the negative log of our concentration of hydronium. And of course, then if we wanted to figure out the concentration of hydronium from our pH, we would do 10 to the negative pH is then equal to that concentration of hydronium, okay? Likewise, we can also determine the pOH. So this P essentially just means take the negative log of. So we take the negative log of our concentration of hydroxide. And of course, we could figure out the concentration of hydroxide if we have the pOH of something, right? We can also interconvert between these two using Kw. So like we defined in the previous slide, Kw is equal to the concentration of hydronium times the concentration of hydroxide. The value for those is Kw at room temperature is going to be 1.0 times 10 to the negative 14th. And so that means that our pKw is going to be equal to our pH plus our pOH, which will be 14. Okay, and it would also mean then that in neutral water, we have a concentration of hydronium that is equal to a concentration of hydroxide, where both their concentrations are 1.0 times 10 to the negative 7th molar. Okay. We can place these then on a pH scale. Here's an example of just basically some of the stuff that we can have. You can actually have negative pHs and pHs that exceed 14. Essentially, if you have a strong acid or base with a concentration greater than 1 molar, you would end up in negative pHs or pHs above 14.0. But just so you know, these are some examples. Bleach is very basic. If we think of gastric juice, it's the stuff that's in your stomach, tends to be very acidic. So yep, that's just something, some examples that you can find in here. Okay. And so just as a take-home point, again, things that are acidic will have greater concentration of hydronium than hydroxide, and they will have a pH less than 7, 25 degrees Celsius. Things that are neutral will have equal amounts, and things that are basic will have less hydronium than hydroxide and a pH greater than 7. Okay, that is going to be the end of our pre-lecture for pre-lecture 13. I hope it was informative. If you have any questions, please let me know, and I will see you in class.